This video will focus on defining the difference between acids and bases in terms of their general characteristics, and then also reviewing how to name both acids and bases. So when you think about an acid or a base, potentially lots of different things come to mind. What I always like to start out with is just kind of grounding you in what you're exposed to every day that could be considered acidic or basic. So for your acids, we've got like most fruits, oranges, grapefruit, grapes, red bell peppers are acidic. Vitamin C is an acid, vinegar is an acid. Okay, a lot of food type items we see listed under acids. For bases, you're less used to what could be basic. Soaps and cleaners are bases. A lot of stomach type medicines, Pepto-Bismol or antacids, those are actually bases. Okay? So you see right away, acids are food products, bases generally are not. Now we have some foods that are bases, pure chocolate, coffee, things like that have base properties to them. So what are the properties of acids and bases? Let's start with some acids. Acids taste sour. So if you go back to that list of things that are commonly acidic, you'll find that they all have a similarity that they taste sour. If you get an acid on your hand, it actually just feels like water though. And while we don't recommend, obviously, nowadays eating anything in lab, something a lot of scientists used to do is actually taste their chemicals to determine what type of material it was. So they would actually taste acids and taste the sour taste and end up with chemical burns in their mouths and things like that. So not just food items are taste sour. If you were to taste hydrochloric acid or sulfuric acid or something, it would actually taste sour to you. But it doesn't feel any different than normal water, which is why it's a little scary and dangerous because we don't know what's in it just by looking at it. In terms of its chemistry, it corrodes metals. As a byproduct, then it produces hydrogen gas, so it bubbles when you have hydrochloric acid with metal. Acids are electrolytes. Okay, they dissociate into water and allow electricity to run through the water, so they're considered electrolytes. Sometimes strong, sometimes weak, but they will make ions in solution. In terms of the pH, acids have a pH of less than 7. Okay, so if you had pH paper or litmus paper or something, you could determine the range for your acids. And actually with litmus paper, just like we were doing in the qual lab, acids turn blue paper red, and that's how you know they're acidic. Acids, as I'm sure you're aware, can cause severe chemical burns. Okay, they essentially dehydrate whatever they come in contact with because they're breaking that water and making that hydrogen gas. And they get hot, right? So they actually create a burn just like you would normally have from like a fire burn, but it's a burn from a chemical. So let's look at bases and compare these two. While acids taste sour, the bases actually taste bitter or kind of chalky in texture. If you ever had pure chocolate, it's like baking chocolate instead of normal chocolate, like delicious chocolate you get from the store, without the sugar, you can definitely taste the bitter and feel the texture of chalky. Different than acids, bases actually feel slippery like soap. So there's this very signature feeling to them if you were to get them on your hands. They're electrolytes just like acids are, so in solution, bases dissociate, creating ions that allow electricity to run through that solution. We got a pH of greater than 7 for bases then, the opposite end of what the acids are. Again, in the qual lab, we discovered that for bases are blue, so they make red paper blue. And then something you may not be fully aware of, I've mentioned it numerous times in class, bases can cause as severe chemical burns as acids. Okay? It just depends on what concentration you're working with in terms of which one will happen. I don't know if this dates me or if you guys have seen it. It's probably an R, but Fight Club had a scene where Edward Norton, his hand is burned by Brad Pitt using a base because lye, which is sodium hydroxide, is used in the production of soaps, right? Because bases are in soaps. So you can get as severe a chemical burn using a base as you can an acid. It's just a question of concentration of the ion once it dissociates in solution. All acid-base chemistry will be done in solution. Okay, your acids and bases are always in water, so be aware of that. We're dealing with all aqueous reactions. And these are always reversible. Okay, they're reversible depending on condition, but they're generally considered reversible reactions. So let's review naming acids. Way back when we did naming, we learned how to name acids, and now we haven't done it since, November. They were the endings, ic and us. Okay? If you name your ionic compound and it normally ends with "ide," if it's an acid, it will be hydro something ic acid. If it's ate, it'll become something ic acid. If it's ite, it becomes something us acid. So if you recall, the "ide" ending came about because you had an acid from the periodic table. The ate ending is that polyatomics that you're used to: sulfate, nitrate, chlorate, carbonate. The ites then are all one less oxygen, and then those end in us for acids. So if we look at these three examples and try to name them, okay, HBr, H2CO3, and H2SO3, we'll run through the technique again so that you remember. Now, one thing you'll see in common with all acids is they all start with hydrogen. When we get into the definitions of acids and bases in terms of chemically, not just their characteristics, you'll see these H and how it basically applies. So it's some anion with a number of hydrogens needed to balance out the charge. In terms of naming it, if you name this just the way it is, hydrogen bromide, because that's the bromine ion, the fact that this ends in "ide" tells us how to rename our acid. Ide then becomes hydroic. So this is normally hydrogen bromide. It will be changed into hydrobromic acid. So those two come on and the hydrogen goes away. This one would have been named hydrogen carbonate. Okay, that's carbonate. So if you have carbonate, the ate ending comes off and ate is replaced with ic acid. So that's carbonic acid. This guy, this would be hydrogen sulfite because sulfate is SO4 and this is one less. So if this is sulfite, ites becomes us acid. So we have to run through and review this again. I'll put a list online of the polyatomic ions again that we'll be using so you can review and rememorize those. You've got to memorize these rules. Ide goes to hydroic, ate goes to ic. I ate something icky, and then ite goes to us. Luckily, there's no fancy way to name a base. Okay? Bases will predominantly all have hydroxide groups. So if you look at all these names and the formulas on the screen, they all have OH, which is your hydroxide group. And then you just create formulas and create names neutralizing charges just like we've done a billion times. So magnesium hydroxide, for example, you get the magnesium ion, you get the hydroxide ion, and then you crisscross to balance out the charges. Now, hydroxide needs to be in a parenthesis to show that you need two of the entire thing. Same thing will happen with calcium. Calcium is plus 2, OH is still minus 1, crisscross, CaOH2. If we did lithium instead, lithium has a plus 1 charge, so it's going to neutralize just 1 to 1, and that's lithium hydroxide. So bases are super easy. They're always with hydroxide, and then it's just a question of balancing out the charge. So number 4, the NH4OH, that's ammonium hydroxide, because that's the ammonium ion. So you just name each piece. Number 5, Sr is strontium, so that's just strontium hydroxide, and Ra is radium, so that's just radium hydroxide. So each time you just name each component of the hydroxide group, and that's all naming bases is. That's it for this one. Go ahead and do the form, and have a nice night.